All right. I hope everybody can hear me okay. Hi, everybody. I hope you're doing well. I hope you're staying safe and enjoying reading day. It's kind of crazy that the semester's over at this point. For those of you who don't know me, I'm Nick. I am now a TA here. This is actually my last semester teaching. So this is a great way to end. So I guess what I want to do today, and what we'll do for this review session is the same thing we did last time, same exact thing. So I have all of the final exams up here. I can pull up WebAssign too. That's not the problem. I can pull up really any questions you want. We can talk about just general concepts and general stuff. If you want me to say, talk about vector fields, talk about like divergence, talk about surface integrals, talk about planes, or something like that. Totally okay. And what I'll do is you either put in the chat here specifically if you want to do a specific problem, or you can just unmute yourself here and go from there. I will have my whiteboard up so we can do problems like that. And again, this is going to be recorded. I'll post this on YouTube afterwards because, yeah, so everybody can see it if you want to review any problems or you missed something or something like that. Totally okay doing that. And okay, so I did already have a question about one of the problems here, and then afterwards I can go over some more different problems here. So the first question that was asked was actually problem 3 on spring of 2018. So I'm going to go ahead and do that very quickly and talk about that. And that is kind of talking about the curl and divergence of a vector field and using the divergence theorem to compute the flux of something. So I'm going to just share my screen if I can, and we will go ahead and try to do that. So again, if you have any questions just as I'm doing the problem, you can either post it in the chat. I'll try to get to it if I can, or you can unmute yourself too at the end. I'll talk about some specific problems as well. So this is on spring 2018. This is problem number 3. And this problem says I have the vector field F here, which is equal to x, y, x squared plus y squared. It's a 3-dimensional vector field. And what my goal is I am trying to, in these problems, calculate the curl, calculate the divergence, and use the divergence theorem to calculate something here specifically. So this is actually it's actually kind of funny. This is actually a really complicated question. I don't think they meant to make C that complicated of a question, actually. I'm starting to realizing that now. I think that was probably a mistake when they made it. But regardless, what we can at least talk about is how do we compute the curl and divergence of a vector field, and then go from there. So the first thing to realize is if we have this vector field F, we can compute a couple different things with it. You know, one thing we do back when we just have 2 vector fields, right, a PQ. If I want to see if this vector field is conservative, which means that I have, you know, a potential function, there exists a potential function. That's the gradient of it. What I can do is I can actually use Scalar theorem to take q sub x, and I want this to be equal to p sub y, and this means that f is conservative. And what's important to note is this is kind of regarding Scalar's theorem here, where I take the derivative with respect to x, and then y has to be equal to the derivative with respect to y, then x. And this kind of satisfies that exact equation here. Now, if I want to do this in a 3-dimensional sense, this becomes actually a lot more complicated. So if I asked you this question, right, if I asked you, you know, is there a potential function such as this is the gradient of it? Well, the thing is, I have 3 variables now. I have x, y, and z. And Scalar's theorem needs to satisfy now phi xy equals yx, xz equals zx, and yz equals zy, right? I have to do a lot of these things. And what's nice is all this can be bundled up in a calculation called the curl. And so the curl of a vector field, curl of F here, which is sometimes denoted as the cross product of the gradient vector and the vector field itself, can be calculated as follows. Ijk here, or I take the derivative of basically these 3 functions in different ways. So I could write this out more formally. If I want to write this out more explicitly, I could say that, okay, the I component is the R component with respect to Y. So R sub Y minus Q sub Z. I never memorized this part, but I just want to at least show you kind of what gets the output here. Then we would get something like the j component, which is p sub z, because I flip this one, minus r sub x. And lastly, here we would get for the k component, q sub x minus p sub y. And you might notice this guy, which is kind of thought about over here. If this vector field over here is conservative, right, we do have that qx is equal to py, so we should expect this to be 0. And what's nice is if a vector field is conservative overall, each one of these components will be 0 if it is conservative. And so we can actually say that if the curl of a vector field f is equal to the 0 vector, specifically the 0 vector, this actually says that the vector field f is conservative. And for those of you who are wondering what the curl actually means physically, it's related to the rotation of the vector field. So curl, basically, if I tell you the curl at a specific point, if I placed an object in my vector field, let's say the curl is in this direction here, and I kind of put it this way, and I kind of place an object, the curl is this vector right here. What it actually is just doing is it's actually just rotating around that axis here. That's what it's doing specifically. So that's what the curl is. It's related to the rotation. So in this problem, we can actually calculate this. I rarely memorize, I don't memorize this part over here. I kind of just calculate it always via this determinant. And so I'm going to do that here. So why don't we go ahead and doing that. So the curl, this curl of f here is calculated by I, j, k. We have the derivative like the x, y, and then z. We have x, y, and x squared plus y squared. And what I'm going to do is I'm just going to calculate this. So the first I component is the derivative of this function with respect to y, which is going to just be 2y. There's the derivative of this function with respect to z, which is just 0. The j component, I'm going to put a negative out in front, is going to be the derivative of this function here with respect to x, because I'm going across there. This is going to be 2x. And then over here, the derivative of this function with respect to z, because z is not there, so this will be 0 again. And lastly here, the derivative of k, in the k component, the derivative of this function with respect to x is 0. The derivative with respect to y here is also 0. And so this entire thing is 0. So the curl of the vector field is 2y, negative 2x, 0. And this is the curl of the vector field, which relates the rotation of the entire vector. Okay. The other thing we actually kind of worry about a lot of times when we're thinking about interesting things to worry about in a vector field is the divergence of a vector field. And the divergence of a vector field, I'll just tell you how we calculate it first, which is considered a dot product here. So curl is going to be a vector because it's a cross product. Divergence is kind of a dot product thing. So we're thinking about it as more specifically a quantity. It is a number. It is how divergent the vector field is. We'll understand what that means in a little bit. But it's basically the derivative of the first component with respect to x, plus the derivative of the second component with respect to y, plus the derivative of the third component with respect to z. And this quantity here has three kind of aspects to it, right? We have that the divergence of f will either be greater than 0, less than 0, or equal to 0. This tells how divergent these sources. So imagine the vector field is a water, okay? And I have this water column that I'm trying to figure out what the divergence is in here. If the divergence is positive, that means more objects are moving away from a point rather than coming in. It is divergent, right, from that point. So we actually say that since that more water is leaving rather than coming in, we call this a source. If the divergence is negative, that means that more objects are coming in rather than leaving from a point. So we consider this actually a sink. And if there's an equal amount leaving and coming in, we call this, it's actually called an incompressible fluid at this point. So divergence free, we sometimes call it. And if the entire vector field is 0, we call this an incompressible fluid. For instance, water is incompressible. Some types of air are incompressible. I know this sounds silly. Yes, we have all these different types of things here. So if I want to calculate the divergence of this vector field here, the divergence of f here is going to just be calculated as the derivative of this first function with respect to x plus the derivative of the second function with respect to y plus the derivative of this third function with respect to z. And so this is 1 plus 0, which is just equal to 2. So the divergence of this entire vector field is actually 2. So every single point is a source. That's a general trend of how you would calculate some of these things.
I have a question about how they did it in the answer key for this one. After they found that it's 2, there's a little star next to, there's like an extra line. I'm not really sure what they're doing there.
Oh, that's part of C there.
Okay.
Yeah, that's part of C there, what they're doing. Because C is incredibly long, and I don't think they actually meant to do that. Yeah.
Okay.
Okay. So with that in mind then, that's that part. And then the third part here is wanting to calculate the flux here of this integral. And the part here is we want to calculate the flux of f, the flux, flux of f across here, x squared plus y squared plus z squared is equal to 9, where z is greater than or equal to 0. We want to use the divergence theorem. I guess the first thing we should realize is what is the divergence theorem here, and kind of how do we utilize this. So the first thing is, what is flux? Right? How do we calculate flux? Flux is a way for us to understand how much fluid is moving through a surface in a given time period. Usually we think about it as a unit time. It's usually dependent on the problem itself. But the idea of flux is how much fluid is moving through a surface, given an orientation of the surface. And we can calculate flux by using this integral here. Okay. Now, in this case, we can calculate this in a couple different ways. We really actually only have 2 ways to calculate this integral, at least in our class, at least at the moment. The first way is kind of the brute force way, where what we do is we parameterize our surface f, and we go ahead and we kind of calculate it as r of uv, and we go through this whole process where we can actually calculate f, the function on my parameterization, and we take the dot product with ru cross rv dA, where this is the normal vector here. The normal vector to my surface specifically. Here, ru cross rv, that would give me a normal vector. That's one way to do it. But the second way to do it, and the more important way, at least in this problem, to simplify things very greatly in this part, is to realize that what we're doing is, if I have a closed and bounded surface, so if f encloses a surface, encloses a volume, sorry, let's call it E, we can utilize the divergence theorem. And the divergence theorem says that I'm allowed to calculate this integral by manipulating it to a triple integral. But what is the integrand? The integrand is actually the divergence of my vector field. Divergence of f dv. And as a reminder, divergence of f here is going to be a scalar function. It would actually be a function. It could be dependent on x and y. It's just rare here that it's actually 2. But it could be kind of doing that. So what we now want to do is see how we can understand and use the divergence theorem here. And I think this problem is actually a little bit complex. You have to kind of consider something. So they are asking here to compute the flux across this portion right here, where we're talking about specifically just the upper half of this hemisphere. So I have this upper half of this hemisphere. I cannot draw spheres very well. I can't draw really anything well, but it's okay. Just assume I have something like this, where this is x squared plus y squared plus z squared is equal to 9. Okay, now we only care, and I know this is going to sound really silly, we're only caring across the hemisphere. So we only care about this portion, this top portion. Now, to use the divergence theorem, I know this sounds silly, and this kind of got a really, really important point here to kind of make. We kind of have two surfaces kind of considered here. And I know this is going to sound silly, but just kind of bear with me for a second. This is why this is a little bit of a more complicated problem. We only care about this upper part of the bowl. Imagine that you have a bowl and you have a Tupperware lid on it, okay? I'm just caring about the Tupperware bowl. I don't care about the lid. I want to know the flux going through that Tupperware bowl. So the thing is, I can't use the divergence theorem unless I consider both the bowl itself, the Tupperware itself, and the lid, because I need a full enclosure. Right? So I need a full enclosure. So what I want to kind of consider is I need to think about this more formally. So let me kind of write this a little bit. Let me kind of write this a little bit more mathematically. We really have two surfaces to kind of consider here. S1 is this circle on the XY plane. Okay, that's kind of my lid of my Tupperware that I'm currently flipped upside down Tupperware. It's kind of falling apart, whatever's in there. And I'm going to consider S2 actually the surface of my sphere here, okay, my hemisphere. So realistically, this surface S here, this flux here, is really two things. I really want to consider F dot ds and this other part of the surface. Now, my goal is just to calculate this guy right here. I only want to calculate this flux because all I care about is I want to calculate basically the flux on my bottom and the flux on my top. But realistically, I want to just calculate this. But in order to use the divergence theorem, I need a full enclosure of my volume. Okay. And so if I have this kind of S1 and S2 here that's kind of enclosing all of that, then what I could utilize is I can use the divergence theorem inside of this domain that I've now enclosed, where this is my full domain that I'm kind of enclosing. So it's kind of two parts here. All I want to do is calculate this guy, but to include the divergence theorem, I need this extra piece because I need the top of the Tupperware. I need the lid on this. Keep feeling like I'm freaking SpongeBob and Patrick. The lid. Sorry that I keep saying that. So now what we can do is we can utilize this like volume here inside of it. We can calculate the divergence of that inside of that. And my volume here, my volume E, is the entire upper half of my ball inside of it. So I can kind of see here, I can rearrange this. I know this sounds silly, but I can kind of rearrange this and move this over, and I can calculate that this integral here, it's actually a really good problem to do here because it actually tackles a lot of really good stuff, is really this integral, where I have two parts. I need to calculate both this divergence part, which is actually going to be very quick, and the second part here, which is the amount of flux that's going through just that lid of the Tupperware specifically. It's a subtle point, but it's it's a really, really important point there to make. And so I'm going to calculate both of these. I'm going to call this 1, and I'm going to call this guy 2, because we have to do two things. We have to calculate 1 and 2, and then we subtract them. So let's calculate 1 first. So if I want to calculate 1, this is actually very quick, because the divergence of F here is equal to 2, right, as we've just kind of calculated. So the triple integral E divergence of F here dV is just equal to the triple integral of 2 dV. And now what's really nice to remember is the triple integral with a 1 inside is just the volume of my entire my E here. So this is actually could be rewritten as 2 times the volume of E, kind of like that. The volume here is just half of a sphere. I know the whole sphere is 4/3 pi r to the third. So if I want to have a half of a sphere, I just divide this by 2. And so this would just become 2/3 pi r to the third. This is that volume here. So my radius here, just kind of going through this, my radius is 3. So this would be 3 to the third. So it would be 2/3 pi to the 3/3 More formally here, this would then become here 4/3, and then, yeah, I can kind of cancel this out. It'll be 4 on top, and then a 9, so it'll be 36 pi. So this first part would be. If only that was it. It is not, unfortunately. Just to kind of work a little bit more. So now we have to kind of calculate this second one. Okay. Now there's a couple of different ways you can go about it. But let me at least tackle one way to go about it, and we'll kind of discuss this here. So I will pull out at the end, and we can kind of view the whole problem as a whole, but I wanted to at least tackle this. Now, as a reminder, what does this dot product actually mean? Right? What does this dot product actually mean? I know this sounds silly, but what does it actually mean? Well, right, it is really saying f dot n df. This n is a unit normal vector to my surface, okay? Now, when you're considering normal vectors in a divergence theorem problem, you always assume the outward normal vector, which means you always assume the vector that is pointing directly away, not into the volume, but out of the volume here. If I'm looking at this, I could actually come up very, very quickly with my, my normal vector here, actually. My normal vector here is pointing straight down, right? My normal vector here, I hope you'd agree, it's just the bottom of the tupperware. It's just pointing straight down like that on S1, right? Just pointing straight down. So if it's pointing straight down in a negative z direction, all this really is my normal vector here. It has to be a unit vector, so it's just 0, 0, -1. And so you can come up with a normal vector very, very quickly because of that. And that's why this is really, really helpful. And again here, my surface that I'm kind of integrating over here is in terms of my x and y, right? In terms of my x and y, which is this 3, and this is 3 here. This is my surface S. This is actually the surface S1 is on this part. So I could parameterize this if I wanted to in terms of x and y, but I really don't have to because I can just utilize this. So this is a polar region. And I kind of want to just write this. I'll name this domain D as well. And what we can do is I can now rewrite. I'm going to actually zoom out a little bit more. I hope you guys can still see that here. What I'm going to do is I'm actually going to now calculate. I know that this normal vector here is going to be 0, 0, -1. I'm going to take the dot product of this with my vector field f, which is going to be x, y, x squared plus y squared, right? That's my vector field all the way up there. X, y, x squared plus y squared. So my normal vector here, now over my domain D is x, y, x squared plus y squared, dot product with 0, 0, -1, dA. And again here, what I could take this dot product is actually very, very quick because this is 0, this is 0. I'm just left with negative x squared plus y squared, dA. Here. Now, I'm sorry, this is still ds, my apologies. This is still ds, sorry. This still is ds, we haven't changed it over to the yet. Still ds. Okay, so now what I want to do is because, and this is actually a really important part of this problem here, because my surface lies on the xy plane, okay? Because my surface lies on the xy plane, this also is considered the area that I'm kind of integrating over, because I can just consider this just in terms of x and y, right? Because this area can be described very, very nicely in terms of x and y because it's literally on the xy plane. There's no z coordinate. So we can actually exchange this for dA here. And if I'm trying to describe this surface, you know, and I'm trying to integrate over this region here, we can actually just change this to polar coordinates, because I think polar coordinates is a much more beneficial way to kind of evaluate this. So we would have r between 0 and 3. We have theta between 0 and 2 pi. That's going to be a really, really nice one. And what we do again, and I think I've taken a little bit too much time on this problem here, so I apologize. I feel it's a really, really good problem just to talk about just in general, because there's a lot of really good important facets here. So I'm going to now exchange this for my polar coordinates. This will become r squared. And since I'm changing this from Cartesian to polar, I do need to put an r here. So I need to add another r, dr, d theta. And from there, you know, we can integrate this out. And I think we can get something probably like I think 81 pi over 4, something like that here, if we integrate this. And so our final answer is going to be this value, 36 pi, minus this one, 81 over 4, 81 pi over 4. Something like that. Yeah. So that's kind of a general idea of this problem. That's why this is kind of a little bit of an interesting one. So whenever you're kind of using the divergence theorem, a couple things to note. First, it has to be a completely bounded domain. Secondly, you can utilize some really, really important theorems here to realize that you can actually evaluate this just using this interpretation of this n here, and utilizing the fact that this is on the xy plane. I know what the normal vector here is. This becomes a really, really easy thing to parameterize and go from there. So it's a little bit helpful there to kind of do that.
For this problem,
oh,
sorry.
No, you're totally okay. I think it's negative 81 pi over 4. Yeah, thank you.
No, I had a different question actually.
Yeah.
How did you know that the bottom surface, like the S1, wasn't included in the entire shape?
Yeah, that's a good question. So it says here, the divergence theorem to compute the flux. Well, it tells me I want to compute the flux across the hemisphere. The hemisphere does not include that middle portion. If I'm thinking about the hemisphere here, I just consider, like, you wouldn't, if I told you the northern hemisphere of the Earth, you wouldn't consider, you know, slicing through, and you wouldn't consider the magma inside of my Earth part of the northern hemisphere, right? And that's kind of what we consider there. Honestly, it's a little bit of a weirdly worded question. I hope they would be more specific on that next time, but that's kind of how you would assume it. Does that make sense?
Yeah, thank you.
This is across the hemisphere. Yeah, no problem. Yeah, the negative's out here for those. I think somebody commented on that. There's a negative out there here. So we're solving for S2 because we're just trying to think about the upper half here, and that because we can't, we're not considering this bottom half here like that. The normal vector again, it just has to be the normal vectors. How do I come up with this? The normal vector here again is going to be always perpendicular or orthogonal to my surface, right? So this is orthogonal to my surface here, and it has to be going outside of my domain. And since this is a flat surface, it's parallel to the xy plane. I know that my vector is going to be orthogonal, so it's going to be going right down like that. And I know this has to be a unit vector. So there's no x direction movement, there's no y direction movement, so it has to be just a 1 in the z direction. And then we have to kind of do a negative 1 there. You could honestly go ahead and parameterize this entire surface, though, if you wanted to. You could parameterize this, go for it, you could do that, and go through the whole process kind of explained over here. You can go ahead and do that. You can get the same exact problem there. Yeah. Okay, any other questions on this one specifically? This is a really rich problem, actually. A lot of really, really interesting stuff that goes on.
I have a quick question about when you did the S1 integral.
Yeah.
Well, how do you know? Because sometimes you add the r dr d theta, like when you transform, and sometimes you don't. So how do you know the difference when to do that?
Yeah. So a good question. So this is you only add this r once I get down to here if I'm always using Cartesian coordinates. If I start the problem here, if I had already up here parameterized this surface with my cylindrical coordinates in terms of r and theta, I don't have to do this down here. But if I get down to here, and then what I want to do is maybe integrate with respect, if I get down to Cartesian and want to transfer the polar at the end, then I have to add the r dr d theta. If you get to dA, basically, and you are still in Cartesian, you still need to you will still need to add the r there. You don't add it if you start off the problem with cylindrical or polar coordinates. Does that make sense?
Yeah.
Okay.
So if we did it with polar coordinates at the beginning, would that normal vector that you found be different?
Yes.
Okay.
Yep, the normal vector will be different. It will, can I come up with it on the spot? I think it's 0, 0, negative r.
Okay.
Actually, it would be. And so because you would get this r squared here, and then you would get like a negative r, and it would come out like that. Yeah. I think that actually
While
does
putting,
that. Yeah.
you were saying, so when we put the r, like converting to like polar, r d theta. So do we just add this r when we're doing in polar coordinates?
So it's only when you're doing it in polar coordinates or cylindrical coordinates. Yes. If you start the problem off, if you had, for instance, like let's say, hypothetically, you had like a paraboloid and you wanted to parameterize your paraboloid here. In most cases, paraboloids, if you're on kind of a circular domain, it's gonna be a little bit easier to use r and theta, right, for your parameterization. So at the end of your problem, when you're actually starting to integrate, you don't have to add the r in this case. You only have to add the r or only add the rho squared sine of phi or something like that if at the end of the problem, right before you start to integrate here, you are changing your bounds from x bounds and y bounds to r and theta bounds, or to rho and phi bounds, or something like that. That's the only time you would add the r there at the end. Yeah. It is a very subtle point, and it's you only should add or change the integration, like add and change the differential here only when at the end of the problem, if you have x and y as a scalar function and you want to change it, you have to go then and add the r there. If you start off the problem with it, you don't have to, because it will already be baked into the problem. Okay. Cool. So what I'm going to do then is somebody had asked I'm going to start with problem 8 here on spring 2017. Yeah, I'm going to do that. 8 on spring 2017. Here, 2017. Yep, spring 2017. Which is talking about work integrals. If anyone else had any questions on that one, let me know. I hope that problem at least makes a little bit more sense now. That's actually a really, really intricate problem because there's a lot of stuff happening there. If you were uncomfortable with this end here and you were comfortable that way, go ahead and just parameterize that surface on the bottom. To parameterize that surface, what I would suggest doing, right? I mean, if you parameterize this surface here, I mean, honestly, what you can do, it's actually not too bad. It's just x, y, and 0, because the 0 is always going to be it's always going to be 0 on the x-axis, on the xy plane, right? And so you could use this, and then what you could do is if you want to use r and theta, you could just replace this with r cosine of theta, r sine of theta, and 0, and work from there. You could also do that too. So this is now problem 2017, problem 8. Which asks the following question. The integral of c y dx plus x dy, where curve c is given by the vector function r of t, is equal to t to the 5th sine of the 5th of pi t over 2, aka very disgusting, 0 to t to the 1. Okay. So we have this problem here, and I want to try to be able to find it. So I am going to now try to figure out and try to work you through the process of kind of thinking about how you might go about this problem. The first thing you should know here is this is a work integral question, right? This is this problem that looks something like p dx plus q dy, something like this. And we have a couple different ways to solve this, right? This is the same exact thing as saying this is a curve f dot dr, right? This is the same exact problem. This gives me the amount of work done to move an object around a curve C over a vector field F. Now, the two questions, whenever you're trying to answer these questions, are as follows, okay? This is something you should always kind of do here. So the first question, the one question you ask about F, and the one question you ask about your curve C. Okay? What you do here is you ask, is it conservative? Conservative. And is it closed? These questions you always ask yourself whenever you have this exact type of problem. If F is conservative or is C closed? If you kind of do this here, you have to have all your possibilities, all your techniques that we've learned in 16.1 to 16.4 basically, so 16.2, 16.4, on how to solve these problems. This will always satisfy exactly what you need. So kind of as a reminder, I'm just going to write this Punnett square again because I really like this Punnett square. So I'm sorry if everybody's seen it a lot, but I really like this. Kind of always thinking about it. So F conservative, again, that means I have a potential function, right? And C closed. Okay. So we have a yes, we have a no, we have a yes, and we have a no. Okay. So if I have a vector field that's conservative and my curve is closed, that means I start and end at my same exact point and I'm conservative. We automatically know off the bat immediately that the answer to this is 0, period. Done. We know this because of actually 2 ways. We actually know it because of this, this one right here and this one right here by the formulas that they give, which are really nice. Well, let's at least tackle that. We can actually see this when we go forward. If F is conservative and it's not closed, what can we utilize? Well, if F is conservative, we know that this is path independent, which means it does not matter how I get from point A to point B. All that matters is how I, just where I start and where I end. And so because of this, we can actually utilize a potential function. So this is actually the fundamental theorem of line integrals, or the FTLI, which says that I know that F here can be written as a potential function, gradient of a potential function. And what I can do is I can just calculate this integral as F phi of the end point minus phi of the starting point. With horrible notation there, feel free to just yell at me about that. But what we do here is we calculate the potential function, specifically the function itself, at the end point and subtract it from the starting point. So it's independent of path. That's what's really helpful about this. It does not matter how I get there. If F is not conservative, but it's closed, we can start to utilize Green's theorem. In the 2-dimensional sense, it's Green's theorem. In 3D, it's actually Stokes theorem. Okay? Which means that you have something like you have this guy, which is the double integral at my domain D of qx minus ty dA. And as a reminder, these two now can show you that this answer is 0, because if it's conservative and it's closed, qx is equal to py. So it goes to 0. As well, the endpoint and the starting point are the same, so this entire thing would be 0. There's 2 ways to kind of mobilize. And lastly, the worst case scenario, if F is not conservative and C is not closed, we have to go brute force. This is brute force method. And what do I mean by brute force method, right? We can then either utilize the fact that the integral of f dot dr here is equal to the integral from A to B. We parameterize our curve, r prime of t dt. I did not make these boxes big enough. Sorry. Well, we kind of utilize this way. Or if I have this dx, right, I could replace this dx with x prime of t dt and dy with y prime of t dt. Those are kind of the processes that I would use. So this Punnett square always works really nicely. If we like our genes, if you want to do a flow chart, it works the same exact way. I like it kind of written like this. So let's kind of check both of these. Is F conservative? Well, in this case, my vector field F is equal to just y comma x. If I look at this, then I calculate this is P and this is Q. Q sub x is equal to 1, and P sub y is also equal to 1. Huzzah! It is equal to each other. They do equal to each other, and so therefore this means that my vector field F is conservative, which means that there exists a function phi, which I'll call a phi, however you want to call it. There is its potential function such that the gradient of it is equal to my vector field. How about my curve here? How about this curve? Now, how do you know if this curve is closed, right? How would you know that? Well, you would know by plugging in your endpoint. If your starting point and your endpoint are the exact same, then we are closed here. So r of 0, if I plug this in, this is just 0 here. This becomes sine of 0, which is 0. This starts at 0, 0 here. If I plug in 1, this is just 1. And this guy is sine to the 5th of pi over 2. Sine of pi over 2 is 1, so 1 to the 5th is also 1. So this is not a closed curve because we start and end at different points. And so we really, if we're looking at this here, if I have my xy, I start here and I'm ending here on this weird curve, whatever this curve is. But it doesn't matter because this vector field is conservative. So I can go in this direction, I can go in this direction, I can go in this direction. It does not matter. What matters is I'm starting and ending at the same point. So what I'm going to do instead now is to kind of complete this question, I now have to compute my potential function. I'm now going to try to evaluate this integral by computing this potential function and then evaluating it at 1, 1 and evaluating it at 0, 0 and subtracting my answers. And so to do this here, we then see that, okay, well, how do I kind of go about this? There's really two big techniques that we kind of use to solve these problems. But what we do is we say, okay, well, my P here is y, x, and we know that this means that this is equal to some gradient of a potential function. Here, something like this. There's a gradient of a potential function. And therefore, this is something like phi sub x and phi sub y. And so this means that the derivative of this potential function with respect to x is equal to y, and the derivative of this potential function with respect to y is equal to x. That's what it's really saying. So because of that, you know, what I want to do is I want to basically get back up to my original potential function. And the way to do that is to integrate. So I'll show you two techniques just to kind of show both of them. They're not really that different. One of them is a little bit more procedural. One of them is a little bit more kind of looking at it and just making a decision. So here, what we see is this one. If I integrate this with respect to x, we'll just integrate this with respect to x. This gets me back up to my original potential function, phi sub x. Integrating this with respect to x, well, y is a constant, so this becomes just x times y. But when I integrate with respect to x, I have to be very careful because you have to think about it. When I take a derivative with respect to x now, if I take a derivative with respect to x, what happens, right? I have a constant. Constants will go away, but also functions just purely of y will go away. So when I integrate, I don't have a constant of integration. I have a function of integration. I literally have this function, which we'll call g of y here. Okay. And now my goal is to find what this g of y is. Because again, if I take this derivative with respect to x, this entire term will go away and we're left down with y. There's two ways you can go about this. One way that I know a lot of students like to do, which is absolutely cool. The first thing you can do is you could say, okay, well, the first technique is, well, I'm going to integrate this guy with respect to x, with respect to y, get back up and try to compare them and see if I'm missing any terms. In this case, if I integrate this function now with respect to y here, phi of xy is now equal to, well, x is a constant, so it just becomes x times y. But when I integrate, I do have this function now of with respect to h. H of x here with respect to x now. And what I have to do is I now need to figure out, well, these two functions must be the exact same. So if they're the exact same, what is g of y and what is h of x? Well, in this case, h of x and g of y are both 0 because they both are, there's no function over here which is explicitly of x. There's no function over here which is explicitly of y. So this goes to 0 too, and this goes to 0 as well. And so therefore, your final potential function, phi of xy, is equal to x times y. The other technique you could utilize, if you wanted to, is if you were at this position, if you started here, if you went, okay, I have phi of xy is equal to x times y plus g of y. Let's say you started here. What you could do is kind of say, okay, I'm going to find g of y. So to do that, I have one other piece of information, which is this guy. So I'm going to take this derivative with respect to y. Doing this, take this derivative with respect to y, I would get this is x. This right here would be g prime of y. And now I know that this function right here and this function right here must be the same because they're both the derivatives with respect to y. And so you can see here that the x's kind of cancel, and this implies that g prime of y is equal to 0. That is not a 0, sorry. G prime of y is equal to 0. And you can integrate this back up, and you get g of y is equal to some constant k. And so realistically, there really is this constant k, but always for our problems, we let k be 0 because it just makes everything so much more simple, which we're allowed to do. And so therefore, your potential function is this. So lastly here, if I want to evaluate this exact function, if I want to evaluate this integral here, this integral then, kind of going all the way around here, this integral then is equal to, this is f dot dr. We know that this integral now can be written as a potential function, the gradient of a potential function. So we say that the derivative, we say that this is the integral now of this gradient of phi. So because of the fundamental theorem of line integrals, we can evaluate this potential function at my end point and subtract it from my starting point. My end point here is 1, 1. And my starting point is 0, 0. And so here, I just plug this in, it's just x times y. So it's just 1 times 1 minus 0 times 0, or just 1. That's my answer. So regardless of how I get from point A to point B here, I'm always going for, I will always take the, I'm always going with the vector field, basically. I'm always, in my amount of work it takes is 1 joule, or however, whatever that kind of is there.
So for this question, since you go straight to doing the fundamental theorem of line integrals where you like the end minus the start, why do we find the potential function if we don't really use it? Is it like to show us that we can use the
We did use the potential function. The potential function is right there, x times y. So I'm just multiplying the coordinates here. That's actually what I'm using right here. Yeah, so just 1 times 1 and 0 times 0. I'm literally plugging in x times y here. If this was more complicated, let's say it was like x squared plus y squared or something like that, you know, I would actually plug in 1 squared plus 1 squared and 0 squared plus 0 squared or something like that. Yeah. Any other questions about this problem?
Do you think we could do number 9 next, which is kind of another like potential function problem?
I was already asked, somebody asked to do that, so I'm just gonna kind of go about that in this part.
Nick,
yeah.
can you just like summarize the whole procedure one more time? Of like, just like how you did the derivative function and all. The last part.
You mean this part right here or this part?
Yeah, that part.
This part? So
Yeah.
what we do, So what we do is we assume that because we know this is a conservative vector field, because we check that qx is equal to py, we know that there's going to be a potential function, which means that the gradient of that function is going to be equal to my vector field. Therefore, we can write that this function right here, this vector field here, has to equal the gradient of something. So that means that the x coordinate has to be related to phi sub x. The y coordinate has to be related to phi sub y. You can write it like this. The technique that most students like to use is this first one that I mentioned, but the second one is also, I like to use, I actually like to use the second one better. It's a little bit more procedural and it's less guessing. But what we want to do is I have phi sub x. So to get back up, I want to get back up to my original vector. I want to get back up to my potential function. So I integrate with respect to x here. Integrate with respect to x, I gain my function. But then when I integrate with respect to x, I always need to add this function of integration, which is with respect to y. And so I need to be able to find this function that's just of y here. In order to do that, one way you can do it is to integrate with respect to y of my other function, which is dependent on it. Integrating this with respect to y here, we get that this is equal to x times y, and then we have this function of x here. At this point, we kind of look on both, and we kind of see, okay, well, they share this xy here. So what is g of y? Well, there's no function here that is just of y. So we know this has to be 0. And similarly, this one has to be 0 too, because there's no function just of x over here. And so because of that, this means that my whole potential function is just equal to x times y. Another way you could have done it, which is you can take this function, you can take this first integral that you did, you can actually take the derivative of this with respect to y, because you have another condition here. So taking this derivative with respect to y, you can then equate it to your other derivative you know has to be the derivative with respect to y, and find out what g prime of y has to be. Once you get that, and kind of equate them and get that, you can just integrate it and get your constant, usually, or whatever function this is. We usually have just a constant, which would be 0. We can let that happen, and we get our original potential function back. And then what we do is we plug in the potential function. We plug in this function with respect to the end coordinate, subtract it from the potential function with the starting coordinate. That's kind of the process you would use. Does that make sense, Sanjita?
Yeah, that makes sense. Thank you.
Okay, no problem. Okay. All good here? Okay. I'm going to do then problem 9 on that, which is finding a potential function for a 3-dimensional vector field. So that's a couple of people that had that question here. Let me kind of just draw this line there. And we'll move over this way. Okay. So this is again now spring 2017. Spring. Yeah, let's not do that again. Spring 2017. Number 9, which is to find a potential function for this. F is equal to y squared cosine of x plus z to the third, -4 plus 2y sine of x, and lastly 3x squared z plus z here. I want to find a potential function for this. Now, in this problem, you are already told that there is a potential function. If you wanted to find that this vector field is conservative specifically, so to find this vector field, to check if this vector field is conservative, if you had to, which in this problem you don't have to, you would have to check the curl of the vector field, right? If the curl of the vector field is equal to 0, this means that F is conservative. A couple of people are asking specifically that, some of these finals over these years have changed, and some of them are more difficult than others. Professors come and go. Professors add things and they subtract things, and it's honestly up to them how they come up with these exams. This exam is a lot more about we give you a problem and I want to see what technique we use. I don't know what these professors want. I mean, it really just depends on the year and depends on that. So these are actually really good problems to kind of do because they make you really think about the processes that you're using instead. They're definitely difficult. So I'm not going to check that this curl of F is 0 here. We're going to assume it is, and F is conservative. So that means that there is a vector field. There's a potential function. There exists a potential function here such that this is equal to the gradient of that vector field. And so this is phi sub x, phi sub y, and phi sub z. Now, in order to see this, what we can do is what I do now is I say, okay, well, this x component is equal to this guy, the y component is equal to this one, the z component is equal to that one. So I'm going to write down all of these things here. So phi sub x, the derivative with respect to x here, is equal to y squared cosine of x plus z to the third. Phi sub y is equal to -4 plus 2y sine of x. And phi sub z is equal to 3x squared z plus z. Okay. Now, the important thing to realize here is I showed you last time to do this problem here two different techniques where you can integrate all of them individually and and then kind of match up. This will not work for this problem, and I'll kind of explain why once we go through it. Because we'll see that there's going to be a lot of mixed terms here, and so the process you would want to do is actually something over here, like this one. I'll kind of explain and go through it as best as I can, and going through this, and exactly why you'd want to do that exact technique. So you start off here. Let's start off with phi sub x. Again, the same exact starting off point. We integrate to get back up to my original potential function. So integrating this with respect to x, we can get that this would be phi of xy here is equal to, well, the integral of cosine is going to be sine, so this becomes y squared times sine of x, plus, well, this is just going to become x times z to the third. And now think about this. Oh, sorry, this is x, y, and z. I should be more specific. This is not just x and y. It's 3 variables. Well, if I'm integrating with respect to x now, well, okay, well, if there was a function just of y, I would have to add that. If there was a function just of z, I would have to add that. But there could be functions of both y and z combined. For instance, if I had some ghost function here, I'm making something up, so please don't think this. But imagine I had some function like this, right? What would happen is this derivative, I take this derivative with respect to x, this would go away because there's nothing with respect to x there. So because of that, we have actually here a function of y and z here that I need to find. I need to be able to find what function of y and z. There might be separated. They might be a function of y plus a function of z. There might be some mixed terms. There might not be any mixed terms. It really just is dependent on, the problem itself here. So you have to assume that they might be mixed. So it might be something like this here. And my goal now is to find this mixed term. Now, the process that we had last time here was, okay, well, I have two more pieces of information, so I'm going to utilize them. This first piece of information I'm going to use is that the derivative of this function must look like this. So let's find that. The derivative of this function now with respect to y is going to be equal to 2y sine of x. This function goes away, and this function now is the derivative of this function with respect to y. Right? This is actually g sub y. I want to be very formal because I can't use prime because it's dependent on two variables. Now this function right here must be equal to this guy, which is -4 plus 2y sine of x, like this. And so if you note here, this means then kind of implying here that g sub y has to be equal to -4. My y's and 4's get mixed up, I apologize, just in advance. So now I have this function, I have g of y is equal to -4. From here, I want to get back up to my original function g, right? I want to get back up to that. And this is a function possibly of both, right? This is a function both of y and z. So I integrate this with respect to y. And this becomes g of yz is equal to -4 times y. But again here, I have to be very careful. I have to be very, very careful because now there could be a function just of z, just of z. Because when I integrate this, right, if I took the derivative of this with respect to y, this would go away. So kind of including everything down here, this now means that my function phi of x, y, z is equal to y squared sine of x plus x z to the third minus 4y plus my function h of z. And now my goal is to find this h of z here. And I have one other piece of information, which is this guy. So let me utilize that. What I'm going to do now is take this derivative with respect to z here. This first part's going to go away. This second part here is going to be 3x squared, 3xz squared. And this one right here is just h prime of z. And now I know that this function here and this function here must match up. And so this has to be equal to 3x squared times z. Did I write this wrong? Oh, sorry, I did. I'm sorry about that. Sorry, this is 3x squared z. I was like, wait a second, I think I did something wrong. I wrote the problem wrong. That was not my mistake. It was my mistake. It wasn't the problem mistake. Sorry about that. So this is 3x squared times z plus z. And looking at this here, we note that h prime of z is going to have to just be equal to z. Which means that if I integrate this, if I integrate this now, this becomes h of z is equal to z squared over 2. And so therefore, adding all of this up, we can then get that our potential function, actually down here, our potential function here is as follows. Phi of x, y, z is equal to y squared sine of x plus x z to the third minus 4y plus z squared over 2. There's a plus k there as well if you wanted it, but that's kind of how you would go about doing it. So the process here, kind of working backwards, kind of thinking this. This is why I really like this other way here. It's kind of a very, very procedural approach because it kind of makes sense. I'm hunting for a function, right? I'm not kind of guessing here. You really can't guess here because of how these mixed terms. We first assume that the x component is with respect to x, second component is with respect to y, third is with respect to z. You would take your original function. When you integrate, there's a function of both the other variables. Because when I integrate with respect to x, there could be y's and z's that go away because they're considered constants. Then I use my second part here, usually phi sub y or phi sub z, whichever method you want to go with. Whichever one you want to start off with, it doesn't matter. I like to just go in order. We take this derivative with respect to y. We get then that I'm solving for g sub y here. We equate, we get g sub y. Get this be with -4, integrating this, we get negative 4y. But when I integrate this function, because it's dependent on both y and z, I add a function of h of x. I add this kind of last function here. Then I now take this function here, and I now have my last part, which is phi sub z. So I take this derivative with respect to z. I equate it to the other one that I have here, find h prime of z, integrate to get z squared over 2, and then we get this guy. We can set this to be, we can set k to be 0. There's this k here. We can set this to be 0 if we want. We're asked to find a potential function, so we only need one. If we're asked to find the potential function or something like that, we would need the k to be as general as possible. I think that's it. Maybe you have any questions about going about that? I know a couple people actually asked that.
I have a question.
Yeah.
So when you get a function of 3 variables like this, are you always going to use all 3 of them in whatever order you choose to solve for there's going to be like 2 unknowns that you're going to add on, like h of z and g of yz?
Yes, you're always going to do that.
Okay.
This will always be the process. This is without fail. This process will always work.
And if you started, okay, and if you started with like phi y, then you would your final answer would be what was originally there, and then what you found from like doing it a slightly different way. But it could be different, right?
No, it would be the exact same answer. You will always get the exact same answer.
Okay.
Whatever one you start. Yeah, you will always get the exact same answer. You'll just get it a different way. If I start off with this, right, if I integrate this with respect to y, I'm going to have now a function of x and z instead of y and z. And you're going to eventually get probably x and z there. You'll get this xd to the third term. I'll be out of there. Kind of like that.
I have a question, Nick. Can you go from like when we did derivative of phi of y, like the 2y sine x plus gy, so did you just take the original phi value and then integrated it like?
So I took this function right here and I integrated that with respect to x, and I took this. And now what I did is I said, okay, this is my original potential function. And I know the derivative of this potential function with respect to y has to be this guy. And so I take the derivative of this function with respect to y. Taking this here gives me 2y sine of x. And then this derivative here with respect to y must be equal to this function specifically. And so therefore, because of this, we can find that g sub y has to be negative 4. And then from here, I integrate with respect to y because I have g sub y. I want to get back up to my original function. And that's how I get this function right here.
Okay, yeah, okay, that makes sense.
You sure? Okay.
Yeah.
Okay.
And this is the better of the 2 methods? Like there's less guessing in this one or less guessing in the other method?
Well, usually, I know this is kind of like a, as it gets more complicated, this method, and down here, honestly, either method, it really doesn't matter. You're probably going to do the same amount of work, just in general. You might do a little bit less work, actually, if you just integrate both of these. You can't use this method here. You actually can't. You have to be very, very careful on how you do it. Honestly, it's very, very difficult to do it. Because you have to consider so many mixed terms and so many just partial terms that might be there. It would cause you a lot of issues, actually. If you integrated all 3 of these, it'd be very, very tough to kind of combine everything. Honestly. So this is the process you would really have to use if you do have a 3-dimensional potential function.
Okay.
Yeah, you could do it in a different way, but you know, it would honestly give you a lot of, I think, a lot more complications rather than just doing it in this kind of procedural method. If that makes sense.
That makes sense.
Yeah. No problem.
So if we have 3 variables, then we should use that technique instead. But if we only have 2, we can use the other one.
Yeah, exactly that. You could use the 2. That's fine. I mean, in this case, it's a little bit easier to see because you only have 2 things to worry about. In this one, you have 3 things to worry about. It's just a lot more complicated because there's a lot of mixed terms that are kind of might be hanging in there.
Okay,
Yeah.
thanks.
Okay. Any other questions, at least here? Okay. Does anybody have a question that they want me to talk about that hasn't asked a question yet here? I just want to make sure that I'm not. If anybody wants to either open your mic or something like that, or ask in the chat. If not, there are some other things I can do here. I just want to make sure that everybody's kind of getting an equal kind of turn here to go at it. So, does anybody have any other question you want me to talk about here?
I just have a quick, this probably doesn't even need like a problem, but I was like looking back at my notes and I saw the component and like projection equations.
Yeah.
Do you think that's going to be like on there? We didn't really talk about that.
Could be. It could be. Actually, I generally don't know if they've been on any of these 4 finals here. I guess I haven't looked at them too deeply here. Not that I can remember. But just at least remind yourself, because those honestly could pop up again. Let's just remind ourselves what that was. I'm happy to just at least talk about that just briefly here, just to remind ourselves what it is. So if I have a vector A, I have a vector B, as a curly vector B like this, and I basically wanted to find, if I shine a light on the top of A here, if I shine a light like kind of down in this direction here, I kind of can think about that the projection of this would be probably this vector right here. And so there's 2 things I would like to worry about. So there's the scalar projection, which we call comp of BA. We call this component, the component of my vector A projected onto B here. Or we think about the vector projection, which is here the projection of A onto B like this. So this right here, the scalar projection is literally the length of this vector right here, is the length of this. The vector projection literally is this vector. And I hope you'd agree then that if I have the vector projection, this is going to be it's going to be a scalar multiple of B in this case. So if I want to find the scalar projection, if I want to find, the length of this vector, I can kind of think about that this is A here. This is the magnitude of A, this length of this vector here. This is going to be the angle maybe between A and B. I had to think about that. And this right down here would be actually the adjacent to the angle, which is going to be a cosine. So the length of this might be something like the magnitude of A times cosine of theta. Cosine of theta. And if we remind ourselves kind of one way, this is kind of a really ugly thing because we rarely know the angle between 2 vectors. We can remember that A dot B here is equal to the magnitude of A times the magnitude of B times cosine of the angle between these 2 vectors. If we know here, if we divide out by B, you'll get that A dot B divided by the magnitude of B here is equal to the magnitude of A times cosine of theta, which is exactly this. And so we can note that the component of A onto B here is going to just be the dot product of these 2 vectors divided by the magnitude of the vector you're projecting onto. We have A dot B divided by the magnitude of B here. Now, if I wanted to find this actual vector here, well, we know actually kind of working with this, if I want to find this vector, we know that I'm actually, going to be in the direction of B. So basically, I want to multiply C times my vector B, some scalar multiple of it. And with that, if I want to try to find this, I want this vector to have a length, right? I want this vector basically to have a length of equal to this, right? Equal to my projection, right? Scalar projection. So what we do instead is we kind of do a stretching and then a compressing. We take this vector, we make it a unit vector. If we make this a unit vector, we now have a vector of 1. Maybe it's something like this. Maybe it's something down here like this guy. Maybe it's like that. And then what I do, maybe that's the vector of 1. I can now make it the vector length however I want it to. So I can kind of multiply it by the length that I want it to, which is A dot B times that vector. So it'll be A dot B divided by the magnitude of B. Or more formally, this can be written as A dot B divided by the magnitude of B squared multiplied by B. And this right here is your vector projection. You take the dot product divided by the magnitude of B squared multiplied by B. And these are the two ways you kind of calculate that. As a reminder, kind of the relationship between these 2 things, the magnitude of the projection is equal to the absolute value of the component. because this could be a negative value, right? A dot B could be negative if the vectors are obtuse. Kind of think about that way. Is that kind of what you wanted to get out there, Rachel?
Yeah, thank you.
Yeah, no problem. That's kind of a weird concept we haven't really touched at all. Projections really didn't show up at all in these last couple of chapters. Projections are just something really kind of interesting. I'm not too sure if they'll show up, but it's never a bad thing to kind of remind yourself of.
Okay.
Yeah. Anything is fair game. Anything is fair game. Because usually we'll have like one problem that's just all vector problems. Kind of remind yourself of that, and they sometimes just throw in like, oh, what's the component here? Or like that. Who knows? Okay. So I was asked here to go over as well. Somebody else asked here to go over fall 2018 problem 2, which is talk about the gradient and the directional derivatives, stuff like that. So we can talk about that, and then we can get to yeah, we can talk about that here. So in this problem, so this is problem 2 from fall of 2018, like that. So I have my vector field f of x, y, my vector field. Wow, this is just a function. The function here, f of x, y, is equal to x squared plus y to the third. I am at, you cannot see this, sorry. There we go, that's a little bit better. So here, I'm going to first off compute the gradient. Part A is compute the gradient of f, which is fx comma fy. And again, what is the gradient? Say the gradient is the direction of fastest increase. Right, the direction that I will move in the fastest increase here is always orthogonal to level curves. Those are two really important concepts that we know that always happen here. And in a three-dimensional sense, they are normal vectors to our surface, our surface here in three-dimensional sense. So the gradient here, derivative with respect to x, is just 2x. Derivative with respect to y is 3y squared, something like that. Now part B here talks about the directional derivative, du of f, which is equal to du of f of at the point 1, 2 in the direction of u, which is 1 over the square root of 2, negative 1 over the square root of 2. Now, as a reminder of what a directional derivative is, this kind of asks, if I move in the direction of u here, how fast is my height going to be increasing? Right? How fast is my height increasing? What's the slope going in that direction? What's the slope of the tangent line going in that direction? As a reminder of how to calculate this, it is just the gradient of f dot product with my vector u. Okay. Now, the important thing to realize here, this is kind of a really big one, is that this right here must be a unit vector. Okay. So it must be a unit vector. And so if this vector is not a unit vector, we will then have to, either just divide it by its magnitude and make it a unit vector. You should never assume, unfortunately, that these are unit vectors. Even though it's a u, you should never assume it. You should always just check it just to make sure. In this case, it is. But we can just check this, right? We can just check this by the magnitude of u here is equal to the square root of 1/2 plus 1/2, right? Squaring this guy plus squaring this guy. This is the square root of 1, which is equal to 1. This is a unit vector. That's cool. So what I want to do then is I want to calculate the gradient at my point 1, 2. So calculate the gradient at my point 1, 2. Here it's equal to just 2. This is going to be 3y squared, which is just 12. And so therefore, we can get that for the directional derivative, the height, the function height is increasing as I move in the direction of u. The direction is going to be increasing or possibly decreasing. And so it's equal to the dot product of 212 dotted with 1 over the square root of 2, negative 1 over the square root of 2. And we see here this will be 2 over the square root of 2 minus 12 over the square root of 2, which is just negative 10 over the square root of 2. And so this is saying that if I move in the direction of u here, I move on that direction instantaneously. It's very, very instantaneous. Right? What's going to happen is my height is going to be decreasing at a rate of 10 over the square root of 2 units per unit. time here as I move. That's that one. So then part 3 here, or part C, I'm going to go more formally. Feel free to, if anybody has any questions or interject here just about this problem, feel free to ask. This part here, it asks which direction is F increasing most rapidly? Rapidly at 1, 2. Well, what's really nice is, again, the gradient gives you the direction of fastest increase. It will give you the direction of fastest increase. So immediately off the bat, what we do is we just give you that the gradient of F at 1, 2 is equal to 2, 12. And that's my answer, 2, negative 12, sorry. No, it's just 2, 12, sorry. No, it's just 2, 12. Right. Yeah, it's just 2, 12. And so that's my answer for that. So you don't really have to show any more work unless it tells you it wants a unit vector, in which case you just divide it by the magnitude of that. If you're not asked the unit vector, that's okay. You can just kind of leave it as kind of a pure form as 2, 12. And so that's kind of that problem. You're not asked for the maximum rate of change, at least in this part. So then what we can do is part D, ask for the max rate of change. What it is, the max rate of change, again, is actually just the gradient of F, the magnitude of it. That's all it is, not the factorial of it, but it's just the magnitude of the gradient of F. And so the magnitude of this vector of 1, 2 is just the magnitude of 2, 12, which is equal to 2 squared plus 12 squared, which is equal to, I think, the square root of 148. I think you can simplify that, but I will leave it as that kind of form there. If you were asking for the maximum rate of increase, it is a square root of 148. If you were asking for the maximum rate of decrease, it is a negative square root of 148. Because the fastest, where it's decreasing the most rapidly is the exact opposite direction of the gradient. So if you're asked to find the fastest rate of decrease, it's negative 2, negative 12. Okay, that's the fastest rate of decrease. It's the exact opposite direction here. And lastly,
Nick,
part
I
E here.
have a question about D really quick.
Yeah.
If you said that the maximum rate of decrease was negative 2, negative 12, would that mean that once you take the magnitude, it would still end up being the same number?
You would have to put a negative out in front. It is actually equal to negative gradient of it all. That's what it would be. Yep. Okay. But you're right. When I square it, right, it would go away. Right, that negative, but I would have to put a negative out in front because I want to think about that. That would give me a decrease, right? That would give me that decrease there.
Okay, sorry.
No, you're good. Absolutely good. That's an absolutely valid question. So here, what I'm going to do, the last one is to find a normal vector for the surface. So my surface here is f of x, y, z is equal to x squared plus y to the third minus z to the fifth is equal to 10 at my point 1, 2, negative 1. I want to find a normal vector to this surface. The normal vector to a surface, if I have f of x, y, z is equal to 10, the normal vector is just the gradient at my point. I'm so used to writing big F's as vectors now in the last couple of times. I'm sorry. But the normal vector here is just the gradient, right? That is the interpretation of it, which is really nice. So this is just equal to fx, f sub x, f sub y, f sub z. And we just plug in our numbers. So in this case, we would get that the gradient of f is equal to 2x, 3y squared, and negative 5z to the fourth. And so I want to find it at this point specifically. So to find the gradient of f at 1, 2, negative 1, we calculate this and we get, this will just be, this first part would be a 2. Second part here would be a 12. And the third part here would be just a negative 5. And so this is my normal vector that would be to my surface here at that point. So if I have a three-dimensional surface, right, if I have a three-dimensional thing like this, that's how I kind of do it. I calculate the normal vector like that. You know, this is kind of the way that you would use to find the tangent plane, right? Tangent plane, if I have a function like this, I have a tangent plane, what I do is I take the gradient of it. I take the gradient, find the point, and then I use that in the a times x minus x0 plus b times y minus y0 and stuff like that to get my formal equation for my tangent plane here. That's kind of all those concepts there. Does that make sense, the person that asked? Yeah. Does that make sense? Tony? Or anybody else that has any questions
Yeah,
on
it
this
does.
specifically?
Thank you.
Cool. No problem. Okay. Cool. What I will do here, I'm trying to see, I have a couple of, yeah. Yeah, so just really briefly, what I'm going to do is I'm going to really quickly go over problem 3 on this one, and then I'm going to answer a question about flux integrals and surface integrals. So I'm going to do problem 3 on this one because we're on it. And then I'm going to just talk about just in general surface integrals quickly, because that's a really, really important thing. We haven't really covered that much in this talk yet. So in this talk, this is not my supposing talk. So I'll do that. So I'm going to do problem 3 on here. Of course, I'm going to take a look at switching bounds, kind of going through that. And then what we'll do is we'll go onto the surface integrals question that Lauren kind of asked there.
Nick,
yeah.
I like have a general question that's not really like doing a problem for, at least for the ones that sometimes ask us to do parametric equations on the practice finals. Whenever they wrote the parametric equations, they also wrote the domain like negative infinity is less than t is less than infinity. Do we have to write that, or is that okay?
If you should always write the domain, always, if you can.
Okay.
It will never hurt you unless you get it wrong. But it will never hurt you if you write it there. It's always really important. If you have a line, for instance, you should always say that it's from -3 to infinity. For line segments, you should have 0 to 1. You should always be as precise as possible when you're doing that, because I've graded these things before where sometimes they take off for that, sometimes they don't. So always just include it, just as a general, just the rule of thumb.
Okay, thank you.
Yeah, no problem. So really quickly, I'm just going to go over how do we switch integrals, kind of going from there. 0y1 f of xy dx dy here. So I want to try to flip the order of this integral right here, just part A I'm talking about. So how do I go about doing that? The first thing you always want to do when I want to flip the order of integration is draw out the region as best as you possibly can. So we see that we have x is between the square root of y and 1, and we see that y is between 0 and 1 here. Okay. Now, how do I draw this? Well, the things you should always draw are x equals the square root of y, x equals 1. Always draw those lines. Always draw these bounds specifically. And if we do that, right, we draw this out. I have x, I have y. Well, x equals the square root of y might also be written as y equals x squared, but I'm just in the x part here. I'm just in the positive x part because and the positive. Oh, actually, no, it's the entire function here. Sorry, the entire thing. So I would get something like y equals x squared, which is something like this, and x is equal to 1. So x is equal to 1 is something along the lines like that here. And then I say that y is between 0 and 1, and thankfully these intersect at 1, 1 here. And so we're between 0 and 1, so it's going to be this domain right down here. I'm going to zoom in a little bit more. So I have been told first that I'm integrating with respect to x and then y. Now what I want to do is I want to integrate with respect to y and then x here. So if I'm integrating this with respect to x, well, I want to integrate this with respect to y. What I do is I draw lines going upwards. So I draw lines going like this, like that. Where do I always enter the region from? I always enter the region from this line right down here, which is actually just 0. Right? I always enter from y equals 0. So I always enter from that region. And then I always exit from this upper line, which in this case I've already transformed into y equals x squared. And so therefore, I have to get a function of x over here, which will just be x squared. And then what we do is I note that my lowest value of x is going to be 0, and my highest value of x is going to be 1. And so therefore, our integral then can be rearranged with respect to y first and then x as 0 to x squared and 0 to 1, f of xy dy dx. And that's how I flip these orders in integration. So the technique always is to draw out this region as best as you possibly can. It's as good as you possibly can. And then just kind of flip it. So in this case, I said x was going first, right? How do I know that this was the region specifically, right? How did I know this was the region? Maybe you may have thought it was a different region. Well, right, if I go in this direction here, the first thing I should hit is the square root of y, which is this function. And the second thing I should hit is 1. So this is my region specifically here. And so I can flip these by making sure that when I go with respect to y now, these must be 2 functions of x or constants. And then x here was between 0 and 1, so like that.
So Nick, could you think of these like if they're given where like for this one x has a function of y in the domain, then you have to switch it so that when you rewrite it, the y has a function of x in it and the x has the constant?
Yes, that's exactly how you should think of it.
Okay,
yeah,
thanks.
That's always how it is. Yep. Okay. All good here. Okay. So what I'm going to do is I'm going to answer this question here, where I am going to just touch upon the different types of surface integrals that we have, kind of like this. And if I am missing something here, Lauren, that you want me to talk about, let me know, kind of in this one. So we have a couple different types of surface integrals that we have, right? We have flux integrals and we have some like kind of area. There's really 2 types of integrals that we have. Really 3 types of like kind of surface integrals that we kind of first off say. So let's assume I have a surface, like a spell surface S here. I parameterize it, let's say, in terms of R of uv, where uv is in some domain D here. Okay. There's 3 things I can really do with it. The first thing I can think about here is the area, the surface area. Of F, which you come down to call A of F. Now, I want you to think about why we might need to, how we maybe could able to do this. Well, I have a vector here. As a reminder, if I have 2 vectors and I want to find the area that they make in a parallelogram, the parallelogram that they make, how would I do that? Right? This actually can be calculated, the area, as the magnitude of A cross B. And so we can kind of imagine that what I'm doing here to calculate the surface area is just taking the derivative of this function maybe with respect to u, derivative of this vector with respect to v, and then calculating the area of each one of those infinitesimal parallelograms that they make and adding them all up to create my surface area. And so therefore, because of this, we can actually compute this as the area, the surface area of the magnitude of RU cross RV dA. We need to take this as the magnitude. And the reason why, right, is because there's no vector field here, so I need to take a magnitude. The next thing you might want to think about is kind of a, I will kind of think about the density of a sheet. Now, what do I mean by that? The density of a sheet, what I'm meaning is let's say I have f of x, y, z. Okay, so I have f of x, y, z. And I tell you that every single point on this, on my surface S has some density, has some kind of density. And I want to find the mass of the object. So imagine I have this cylinder here, this fun water bottle. I tell you at every single point here at f of x, I kind of tell you specifically the density of the object. Maybe there's some different material here, maybe there's some different material down there. That's the best way I get net density if it's negative or something like that. It's kind of a weird thing to think about. So just bear with me because that's the best interpretation I can kind of give you of that. You would get something like this. The mass of the object would be some integral like this, f of x, y, z dx. Now note here that this is a scalar function. This is specifically a scalar function here. So if I want to transform this in using my parameterization here, I do not, under any circumstances, want to, take a vector or multiply a vector by it, because this is a scalar function. This could be something like x squared plus y squared plus z squared, for instance. It would make no sense for me to take a dot product. So what I want to do is if I'm trying to integrate this over my domain D now, I replace my F with R of UV. So everywhere where I kind of plug that in, R of UV. Sorry. And what I'm going to do instead is to kind of think about that I'm going to replace this ds here with just this exact function right here, the magnitude of RU cross RV times dA, because this is really thinking about like a surface area, right? A differential, a surface differential is just thinking about the area of that surface, and the area of that surface infinitesimally is this guy. So I need to replace this with the magnitude of RU cross RV dA. It would make no sense for me to use RU cross RV, because just RU cross RV, because I would have a vector multiplied by a scalar, and I'm trying to get a number out of this. So if I integrate that, that would be a vector, which wouldn't make any sense here. So that's what you can kind of consider like a density of a sheet. So actually, this would be like the mass. This whole thing would be the mass of the object with density f. If this was negative, you can think about it like a net density. It's kind of a weird thing to think about. So just assume that if it's always positive, it's always considered a density or a mass, and the full thing is a mass. And lastly here, we kind of have this idea of a flux integral. So this means I have to have a vector field F. And I am trying to figure out how much fluid is moving through an object. Okay, how much fluid is moving through an object with an oriented surface F. So an oriented surface meaning that I have to tell you a direction I'm going in. Because every single time I think about a normal vector, I have to now tell you the orientation of it. Is it going in a positive direction? Is it a negative direction? Which direction is it going in? Because I could think about maybe water's flowing this way or water's flowing this way. And I might be able to think, I might have to think about that. So the flux can be calculated as F dot n ds here. I'll write this F more formally. Where F here is the vector field, n here is the unit normal vector, or the unit normal, we sometimes call it. This is the unit normal. Unit normal is the vector that's orthogonal to my surface. That is a unit vector, so it's a magnitude of 1. We also sometimes write this as a shorthand as this. This is sometimes also written as a shorthand like that. To calculate this, what we want to do is you have to think about that I want my normal vector. As a reminder, what this normal vector can be calculated as, we can always calculate this as RU cross RV, right, in my parameterization. So with that in mind, I want to consider this as a dot product, right? So I want a dot product. And so to evaluate this, what I do is I plug in my parameterization for F here, and then I take the dot product of RU cross RV here, dA. Because why would I do that? This is now a vector. This is now a vector. I want a scalar. I want this to actually be a scalar value so I can integrate it and use my integration technique. And so because of that, that's why we have these three kind of integrals. So these are the types of integrals you would have. For this flux integral down here, just kind of as a reminder, if I do have a volume that is bounded by S, right, as we kind of had started off the entire time from here, if S encloses a volume E, we can then evaluate this using the divergence theorem. And we can say that the amount of fluid going through an object is related to the divergence of the vector field, which also talks about how much fluid moves through my field here. And so that's kind of what I'm going to kind of get that. So honestly, if you're asked for surface area, you kind of always have to use this, just the area of a surface, right? Area of a surface, you would kind of use this. This, they would never really ask you formally, like what the density of it is. They would just give you this, like calculate something, right? Calculate this double integral of like x squared y squared plus y squared plus z squared dx. You're just gonna use that. The flux, you would always be asked, what is the flux through this? And you would also ask, what would the flux through this would be? To use this one though, you need to have a fully enclosed volume. That's kind of the process here that you would kind of be imagining. Lauren, does that answer your question there? I don't know if I've asked answered your question there. A really, really deep question. So does that make sense?
Yeah, it was good. Yeah.
Okay, cool. Does anybody have any questions about this kind of topic here? because this is a really, I mean, this is really, you know, there's a lot of really interesting stuff here, and there's a lot of material, especially in this kind of chapter here, this last little part. I totally understand. Does anybody have any questions about this here? Okay.
Just
Yes.
so would they, I'm guessing they would either tell us if it's an enclosed volume, or is that something that we might have to calculate?
Yeah. So you know, one thing, they'll almost always tell you, or at least infer, that you're going to be using an enclosed volume. At least here, they would kind of say, you know, you'll at least note, and that's kind of the interesting thing. So let me kind of, I'm not saying words at the moment. Let me try to say them. They would not tell you. They would either tell you two ways. They would maybe tell you two ways that you're going to kind of maybe infer to use the divergence theorem. They would say something like, calculate the flux of this over the surface S, which encloses the paraboloid like this, or encloses the full sphere. They'll kind of mention that. Or they'll say, calculate the flux through this surface. And they'll have like two surfaces maybe, or they'll just go with or they'll just give you a surface that's already completely enclosed. Here. Those are really the two flavors of times that you would know to use the divergence theorem. Does that make sense?
Yeah, it does. Thank you.
Okay, no problem. So again, here, when we're kind of thinking about, at least in this question right here, when would we know to use any of these? Here, if you're asked for the surface area of a surface, you use this formula. Done, always. This one, they would never go find the density. They would always give you something like this, and then so you just kind of go from there. If you're asked for the flux, you always use this integral. This is the flux integral always, period. If you have just an open surface that doesn't enclose anything, you have to use this method. If you have something that's enclosed, you can use this method. Both methods always work. Sometimes it's just a lot easier. I hope you see that the divergence theorem questions make things disgustingly easy sometimes. So it's got a lot of easiness there, which is good. I actually still use the divergence theorem in my research because it's such a handy tool. That's kind of how you should figure out how to kind of deduce each question there.
Nick, I just have one more thing, sorry.
Yeah, very good.
So like when you're parameterizing it with U and V, does it always have to be with U and V, or can it be like X and Y as well?
Whatever variables you want.
Okay.
Yeah, you can do X and Y, R and theta, C and theta. It does not really matter. This is just as general as possible. That's why we use U and V.
Okay.
We're just going to use that just because we don't know what variables you're going to parameterize with, so we just make it as general as possible when we're writing out the general formulas. Yeah, not necessary at all. If they, and again, I will fight teeth and bone if they say like, oh, they don't use U and V, unless they tell you to use U and V, in which case use U and V. But they would not restrict. I doubt that they would restrict you there.
Okay, thank you.
Yeah. Okay. Where else should we want to go? Does anybody have any other questions here that they want to talk about, just in general? Here.
Yeah, would you mind doing the same review but with line integrals? Like do like the same sort of review in general?
Yeah, actually, I think I have a box. Hold on. I do. It's right there. Yay. Okay. So, yeah, so at least here I can add on to this. I've already written this, which is cool. So this is all for work integral. So this is again here, this is for integrals something like this, f dot dr or p dx plus q dy, something like that here. So if I have integrals like this is always the techniques that you kind of use. And this is the exact formulas that you kind of use for those techniques here. And when you would use each of these techniques. So if the vector field is conservative and the curve is closed, those are the two questions you also ask. I love this square too. It's one of my favorite types of shapes. I can make it a pentagon or something like that if you want. So if my vector field is conservative and C is closed, we always are going to get 0 for this integral, for this work integral, always. This talks about the amount of work it takes to move an object around a vector field. if my vector field is conservative and I'm not closed, well, I know that this means my vector field is path independent. So that means that we have to just calculate our potential function, and we go from the end point to the starting point, and we just subtract the potential function's values at the end and starting point here. If my vector field is not conservative, well, I have two options. If my curve is closed here, then we can utilize Green's theorem or Stokes theorem, whichever one, depending if I'm on 3 dimensions or 2 dimensions here. And so that means I can evaluate the integral inside of my area just by doing qx minus py. And lastly here, if I don't have any tricks, like if it's not conservative and it's not closed, I have to just use this brute force. So either if you have something already in the form of f dot dr, you then integrate this by parameterizing this with respect to r of t. You plug in your vector, f of r of t, you take the dot product with r prime of t. If you have something of the form like y dx plus x dy, something of this form here, and you don't want to go ahead and do r of t instead, you still parameterize it, but again, we can replace dx here with x prime of t dt. We can replace this dy with y prime of t dt. That's kind of how we replace these instead. There are other two types of integrals that you might see. The two other types of integrals that you might see here, types of line integrals, you might see something like this, f of xy ds. This again is the net area of the curtain, that kind of says, okay, well, think about the double integral, right? The double integral kind of represents volume. F of xy, imagine I'm calculating at every single point of this curve, kind of the height on this entire curve. I'm kind of making the sheet here. And so this is kind of the area of a curtain, if you want to think about it. And the way we calculate this, right, is that I can replace this ds in the same exact way, actually, very, very similarly to this guy. Whenever I replace ds, I change this with the magnitude of ru cross rv dA, but I don't have to go that far. All I have to do here is exchange this. I'm going to erase this big green line quickly. Here, which we replace this with the magnitude from a to b of f of r of t, and we multiply it by r prime of t dt here. And again, why do we do that? Well, in a similar way, we again have just a vector. We don't have a vector, we have a function. And so I don't want to multiply it by a vector. So what I do is I replace my ds with the magnitude of r prime of t dt here. And I kind of get this exact thing. If I had something of the form fxy, as I kind of mentioned dx here, instead, so like half of a work integral, like this. Again, what I could do is I could replace this from a to b. I would again replace this with r of t here, but I would multiply it by x prime of t dt instead. I don't multiply it by the magnitude of it. I replace the dx with x prime of t dt, something like that. And that's kind of what you would see. These are the types of integrals that you would kind of notice. And there's a lot of parallels I hope you are kind of seeing between these one-dimensional integrals, these kind of curve integrals, and these surface integrals here. Does that answer your question there? Is that what you're getting at?
Yeah, thank you.
Yeah, no problem.
Nick, for that last one, the f of x and y dx, if there was a plus and then f of xy dy, would it just be plus f of r of t times at y prime of t?
Yeah, so up here, for instance, if I had something like this, right? What I would do is if I was in this problem that we did, we showed that we showed that this vector field was conservative, so we don't have to use it. But if I wanted to go brute force, right, I would replace this. If I had something like p dx plus q dy, the integral, what I could do is I could replace this integral from a to b of p. I replace all the functions here with x, my x of t and y of t, and I multiply it by x prime of t. So I'm replacing this dx with that, and I would add it to q of x of t and y of t, and multiply this by y prime of t dt, something like that. Something like that here, right? Where what I would do is I replace this dx with x prime of t, replace this dy with y prime of t dt. Does that make sense, Alonzo?
Yeah, thanks, Nick.
Yeah, no problem. So if F is conservative, and C is a closed, oh yeah, if F is conservative and C is closed, it's just 0, actually here. It literally is just 0, thankfully. And you could see this actually in 2 ways, right? If I have a closed curve here, if I want to use the fundamental theorem of line integrals, right, I note that if I'm a closed curve, my starting and end points are the same. So this goes to 0. This always is actually 0 here. And this is brute force. So if my F is conservative and my C is closed here, this is just my brute force method. I just have to kind of go through that. Yeah, so that's kind of what we do. And these are kind of the process we kind of go through. Okay. So with that in mind, I'm going to come back. I'm going to try to find, this is, again, I am not very good with an infinite whiteboard. I should never be trusted with an infinite whiteboard because I have no idea how to structure this. I'm up there now. Okay. So just really quickly, before we get to more problems, somebody asked a question about the difference between like lines here. So if I'm parameterizing, if I want to find the equation of a line, what's the difference I guess between these two? This was a question that was asked. Equals. So this is actually the equation of a line. This is specifically the equation of a line, where R0 is one of my points on my line, and V is a direction vector. This right here, I have to put a domain here actually, because this is a line segment between R0 and R1. And what do I mean by that, right? If I'm drawing this out, and I have a point here, and I want to go to a point here, this right here is R0. This right here is R1. And so this right here is this line segment from there to there. We always have this between 0 and 1 because if I place a 0 into here, I hope you would agree, if I place a 0, this would just be R0 because this would go away. So I'm starting at that point. At R1, this is when time is equal to 1 because this entire thing, 1 minus 1 would go away. I'm left with 1 times R1 like this. Okay. What's the difference between these two? You can actually get this formula by using this exact top equation, just by restricting it, by noting that your direction vector would have to be geometrically R1 minus R0. Geometrically, that's what this direction is, R1 minus R0, just subtracting these two vectors, kind of as we usually do to find direction vectors. But we would restrict it just between 0 and 1. That's the main difference between these two. Yeah. So good question. If you ever have anything that's negatively oriented in a curve, so I guess just really quickly here, if I ever have a negative orientation, so for instance, you might have like an integral like this, right? Where maybe I want to maybe, use Green's theorem, or maybe you wanted to use, no, I mean, in this case, let's say I want to use Green's theorem here, for instance. But I told you though that C is negatively oriented. Like, what would you kind of do there? The important thing to realize here is at least this kind of concept. If I am going from point A to point B on this curve, and I want to find out how much work it takes for me to go to point A to point B, and I go the exact opposite way to find out how much work it takes for me to go from B to A, you can always find it's going to take me the negative amount of work in that case. So if it takes me 5, the amount of work it takes is 5 from A to B, it would take me -5 to go from B to A. The way we can kind of write that, just as a reminder, kind of write it like this. This negative here is kind of denote the exact opposite way. Here. So for instance, what we do is if I have a curve that maybe is closed, but it's negatively oriented, so maybe I'm going in this direction here, but I want to use Green's theorem, I could still use Green's theorem. But what I would do is I would kind of use exactly this process here. So what I would say is, okay, well, if I want to calculate this guy, it's just actually equal to negative Green's theorem here, qx minus py dx. That's kind of how you kind of handle that, at least in this case. So if you want to use Green's theorem and you want to just kind of use that, you kind of flip the orientation around by just putting a negative out in front of your area integral there. At least that concept. If you had both going in a positive and negatively oriented curve, that's a really, really difficult question. And I have never even come across that even remotely close in any kind of final. If they do ask that, I think that's an extremely unfair question. But if you had something like this, where you had a problem where you had this domain, kind of like this, you have to make sure that everything's kind of oriented. The idea of orientation kind of stems a lot from how I know something's positively oriented. Well, what it means is if I have a closed curve and something's positively oriented, if I am walking on my curve and I face to the left, I need to be looking into my domain. That's the general idea of positive orientation in any dimension, actually. So if I'm walking on my curve and I turn to my left, I need to be looking into my domain in some capacity. In similar way, in a flux integral, if I'm going around my curve, I need to be following the right-hand rule. If I want to go the exact opposite way, if I maybe do that, I just put a negative out in front. That's always how we talk about and handle negatively oriented curves. Yeah. Does that make sense, Kara, there? Does that make sense? Yeah, cool. Cool. Okay. So yeah, what we could do here is we could go ahead and do some of the line integral stuff. There's a couple of questions here on question 6 that somebody's asking about the line integrals. So we can go ahead and do that as one of our last things, kind of more formal stuff here. So what I can do here, I will move over in this direction. So we're going to do problem 6. So this is problem 6 from fall of 2018 here. I'm trying to consider part B here, which kind of says I want to calculate this work integral. Well, my vector field F is equal to yx, and C is the line segment. From 0, 1 to 1, 0 here. So I want to be able to find a parameterization for my curve C and use it to evaluate this line integral. So I know this sounds silly because we actually just kind of did a problem actually very, I know this sounds silly, but kind of if we look back at this, where is it? It's actually the same thing as this. Because it is a conservative vector field. It's yx again. So they want us to actually go through the full thing. Boo. They want us to use brute force method. That's all right. They want us to go through that whole process. It's okay. We actually know that this is actually a conservative vector field, right? So we could use it, but a line segment's not too bad. Right? Line segments are okay. So they're not too bad to parameterize as is, so we can work with it. It's fine. So in this case, right, if I want to use this brute force method, I want to just remind ourselves that what we do is we take this as the integral from a to b of f of r of t dot product with r prime of t dt, right? That's kind of how we do it. So I want to parameterize my curve C, which is this point where it's going from 1, 0 and 1, 1. So we're going from 1, 0 to 1, 1. So it's in this direction here. It's this line segment. We're going in this direction. And what I do first, and this is always the process we use for this first thing, the first thing we do is we parameterize. I can spell parameterize R of t. In this case, we're going to use a line segment because it's just a line segment here. So we can utilize the formula 1 minus t times R0 plus t times R1. This is 1 minus t. My R0 here is my initial starting point, which is going to be 0, comma 1 plus t times 1, 0. And seeing this, we're going to get here, this is a 0, 1 minus t plus t, 0, which is equal to t, 1 minus t. That's one of my parameterization. Now think about what I need here, right? I need to take the derivative with respect to with respect to t here. R prime of t. I need this guy, which in this case is really easy. It's just 1, negative 1. Then I need to do f of r of t, which is also kind of nice. It's not too bad because what I do is I plug in wherever I see x, I plug in t. Wherever I see y, I plug in 1 minus t. So this just becomes 1 minus t, t, because y is 1 minus t, x is t here. And so therefore, what we can do then is this integral will then become, I want to just evaluate this. This integral will become 0 to 1 because this parameterization is important to note. This time was always between 0 and 1. I didn't write that. I should have. This will then be the dot product of 1 minus t and t, dot product with 1 and negative 1, dt. This will just be 0 to 1 of 1 minus t dt, which is 0 to 1, 1 minus 2t dt. And so this is just the integral of t minus t squared over, no, actually just t squared. T squared, by the way, between 0 and 1. And this is just 1 minus 1, which I think is 0. Yeah, I think it's just 0. That's kind of nice. We could have done this again with noting that this is a conservative vector field, right? We could have just used the potential function, and we could utilize that too if we wanted to, in the same exact way. Yeah.
Nick, so for the way, can I ask a question about the way the practice example has it for a solution? So they did just f dot dr, and they used f as just being what it was, y and x, and then they said dr was dx comma dy. Is dr always going to be equal to dx dy?
That is the definition of dr.
Okay, so then they get that from just taking. Okay, I think I get it. They just did it a different way, but you could do it either way, pretty much.
Any way you want to do it. Yep. What they did there was they just said, okay, well, I know I can write this equation right. I can just evaluate this with respect to x because I know x can be really, this could be really, really easy parameterization with x. Because I know I can write this line as y equals 1 minus x, for instance. And I could utilize the fact that dy would be equal to just y prime of x dx there. I kind of work with that. Yeah.
Okay. Thank you.
So yeah, whichever way you want to do it, there's not really a wrong way. I mean, if you want to think about it that way, that DJ kind of wrote it. I think it's actually Dr. Raymond writing that that answer key. That's totally okay. This is also a completely valid argument as well. Any other questions here? The kids are on this one.
Is
Okay,
this closed? Sorry. Is this a closed, like, curve?
It's not. Because we're starting and ending at different points. It just somehow happens to be at 0. That's just a complete coincidence.
Okay. Okay.
Yep. It's not necessary that sometimes it just happens that you have an equal amount of vector. You have an equal amount of going with and against the vector field as I move from A to B, and it's not a closed curve. It could happen.
Okay. Thanks.
Yep.
Nick, for one of the questions on another one of the exams, they asked for the unit tangent vector. Is that always equal to r prime over the magnitude of r prime?
Yes.
Okay.
Yep.
That's like the TNB
Exactly.
stuff, right? That we did.
That's TNB stuff, right? Exactly that. You have the unit tangent vector is just the derivative of your parameterization divided by the magnitude of it. Yep.
Okay, thanks.
Exactly that. It is 7, but does anybody have any other last little questions here that I could answer? Tomorrow we're having a 3-hour extravaganza, so feel free to join us for that. Does anybody have just any general questions that I could answer right now? Any burning questions that they have that really need to be answered by tonight or something like that? Or any general questions? I could stick around for like another 5 or 10 minutes though, if you need to. Yeah, no problem. I'll stick around if you guys have any other questions then. Feel free, if I mean, I'll stick around if you have any other questions, but feel free to leave if you need to. I hope all your other finals, I think finals start tomorrow, I want to say. So if they do start tomorrow, good luck on all of them, if you have them. And I know that we were getting some information about the final, so I think DJ will probably, and Mo will send out some information about the finals and all that important stuff, at least logistic-wise, what's going to happen on Thursday morning. Just be on the lookout for an email if he hasn't already sent that out. And yeah, I'll stick around though if you have any questions.
Thank you.
No problem.